Hello everyone, welcome back to my channel. It's Xylose here from Thriving Academy. Today's video, I'm going to show you how to write configuration of monosaccharides. So in my last video, you see I had been dealing with sugars, with monosaccharide, writing them there and there. So today I'm going to show you how you can basically write all those structures that I use in my videos at this. I have a very special code for you that will help you to memorize all those structures and to master them in no time. So if you are new here, please subscribe, and if you are a returning subscriber, I appreciate your presence, and please keep supporting us by liking, commenting and sharing our videos. So let's get started. So the configuration of monosaccharides can be written using Fitcher projection and can also be written using the Harworth projection. So Fitcher projection is a kind of two-dimensional configuration of a three-dimensional molecule. So basically Fitcher projection is a kind of planar projection. So it's a kind of a kind of an open chain presentation, right, of the monosaccharide of the sugars. So the Harworth projection is a kind of a cyclic projection of three-dimensional configuration of the monosaccharide. So this is an example of Harworth projection, and this is basically a glucose. Okay, so this is also the example of Fitcher projection, and this is Glyceraldehyde. Okay, so in this video I'm going to specifically restrict to writing the configuration of monosaccharides using the Fitcher projection. Okay, so let's see how we can basically write the configuration of monosaccharide using the Fitcher projection. So I'll start with the configuration of D-aldoses. So these are some of the example of D-aldoses: glyceraldehyde that we'll see in previous slide, threose, ribose, and glucose. So I'm going to show you the easiest way at which you can draw these structures on your own. So the first thing that I want us to figure out is that this first carbon is always the same for aldoses, right? And I think we learned this from our previous videos. So aldoses always have this as the first carbon. So the first thing we are going to learn is CHO as the first carbon of all aldoses. And let's take a look at the last carbon. So the last carbon is always CH2OH, 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 right? So we mean that the last carbon is always CH2OH. So next thing that we are going to try to understand is all of these molecules, they have hydroxyl group and a hydrogen group. Okay, and that is where the distinction comes. So let's have this analogy now. Here is the left side of this molecule, okay, and here is the right side of this molecule. So what this is saying is that this OH group, if we consider only this hydroxyl group, it means it can be either attached to the right or to the left. So when we know the position of this and we know it is to the right, so automatically hydrogen is opposite, right? So when we know the position of the OH, we know the position of the hydrogen as well. So if you can take a look at this glyceraldehyde, it has only one OH group, right? I'm not referring to the methyl hydroxyl, a hydroxyl group, a single hydroxyl group. So it have only one and it is to the right. Okay, so in this it have threose have two hydroxyl group, one to the left and one to the right. That means I have one left and one right. Okay, so in this one I have one hydroxyl group to the right, one hydroxyl group to the right, another to the right. That means 3 hydroxyl group are to the right. Okay, and here I have one hydroxyl group to the right, one hydroxyl group to the right, two hydroxyl group to the right, 3 hydroxyl group to the right. So what is this all this telling me? This is telling me that majority of the hydroxyl group in monosaccharides, or specifically in aldoses, is to the right. So anytime I am writing a backbone, like for example I want to write glucose, for example this is glucose, don't mind the arrangement. Okay, so I know the majority of my hydroxyl group are to the right, so I want to find that specific point of difference, and in this regard I want to know the position of this one that make this sugar differs. Okay, and this is how I can basically manipulate and okay, this sugar have OH to the left at this point, and that is why it is called as sugar, for example. So based on this analogy, I developed a formula which I always used to be basically playing around with those monosaccharides, and that formula is called TNCP code. So what does this TNCP code actually means? I am using this T to refer to the type of monosaccharide, type of the sugar. So basically based on the functional group, you know, we have two types of the aldehyde or ketone. Okay, so in creating my code, because I cannot be using all these names aldehyde and ketone, I use A for aldehyde and K for ketone. So whenever I have A, for example, so I know I am going to write an aldose monosaccharide, right? And I know my aldose monosaccharide have always this kind of arrangement in the first and the last carbon. Okay, so I have this already in my mind. So next thing is the N, and this N I'm using it to denote the name of the monosaccharide that I am interested in writing. So in this regard, because this monosaccharide is one that I'm going to write and it is glucose, so I'm going to write glucose in my code. But because I don't want the code to be that kind so long, so I'm going to use only the first 3 letters, right? So I have A glu, meaning an aldehyde glucose. Okay, yeah, name of the monosaccharide, name of the sugar. So next one is the C, which I am using to refer to the carbon length, the length of the carbon, how many carbon atom basically are found in that monosaccharide, in that sugar. So in case of glucose have 1 2 3 4 5 6. So my carbon length is 6, so I have A glu 6, meaning an aldehyde glucose with 6 carbon. So next thing, the final thing is P, which is the position of difference. Okay, and what do I mean with this position of difference? Basically the position of difference is referring to the point at which that sugar is distinct. Like I always assume that all my OH group are basically to the right, okay, because majority are to the right. So I'm looking for that point that it is to the left that make it different, or if they are to the right, I will know how to write the code. So based on this, I have L to mean the left, sorry, L to mean the left, and R to mean the right. When the OH group is to the left, I'm going to use L. When the OH group is to the right, I'm going to use R, and then attach the R to the number of the carbon. So in this, what I mean is that in glucose, I know carbon number 1, carbon number 2, carbon number 3, my OH is to the left. So I have and at carbon number 3, L3. So my code for glucose will be Ag6L3, meaning in carbon number 3 my OH is to the left, so I can basically write all the remaining OH to the right. I don't want all the OH are to the right, so automatically the other side must be filled with hydrogen. So the question is, what if in a sugar there is no free OH group, for example? So when a sugar have no OH group free, for example, that we can see in ketosis, I use N. That means instead of L either to left or to right, I use N, and this N refers to none, meaning there is no free hydroxyl group to that sugar. Another thing that I want you to keep in mind is that when the sugar have all the OH group to the right, all the OH group are to the right, so I am going to use A, meaning R, right, and A all, meaning all the OH group I'm going to write them to the right. So we can see this, how we can basically act this N and A in our when we start the TNCP code. So let's see basically how we can use this code to write the structures of sweet sugars. So I have examples for you. The first one is glyceraldehyde. Okay, so the code for glyceraldehyde, sorry, technical problem. So the code for glyceraldehyde is A-gly3RA, where A is representing what? An aldehyde. Okay, so I'm going to start with my aldehyde backbone. Okay, so this is my aldehyde backbone. I know all aldehydes. Whenever I hear the name aldehyde, whenever I see the name A, aldehyde, this is the first thing that comes in my mind, the first and the last carbon. Next one is gly, which is glyceraldehyde, 3 carbon. It means that what? It have 3 carbons. So already I have 1 here, 2 here, so I need to have only the third one. Okay, yeah, so it is 3 carbon. Then R, that means OH is to the right all, okay, in all the remaining carbons. So my only remaining carbon is this one, so I have OH to the right, and automatically I know I have my H to the left. So you see, by this, okay, I know that immediately when I have OH to the right, 3 carbon is glyceraldehyde. So next one is Ephedras, right? This is a code for Ephedras. A always stands for an aldehyde, so I will first have my aldehyde functional group here, aldehyde backbone here, drafted, and next one is Ephedras. The CHR is just telling me Ephedras, so I know that I'm writing this for Ephedras. So 4 carbon, meaning it have how many carbon? 4. So I have 1 already, 2, 3, and the 4th one attached. Okay, so I know that majority of my OH group are to the right, so my position of distinct of difference is L2, meaning left in carbon number 2. So I'm going to just go to carbon number 2, this 1, 2, left, and then the remaining I have my OH. Okay, and then automatically I know the other side is a hydrogen. So you see, it's quite very simple. So next one is erythrose, right? This erythrose. So I know my aldehyde functional group will be something like this. This is my aldehyde backbone. I have something of this nature. Okay. Then eri to refer to erythrose, 4 carbon, meaning it have 3 carbon. So I have 1 already, 2, 3, and the last one attached. Okay. Then R, A, meaning right, OH, right, and all. That means all of my OH are to right. Okay, so I know automatically the other side is hydrogen. Wow, it's quite interesting. So you see how the TNCP code is quite making it easier for me to be writing and playing around with those monosaccharides. So next group are the pentoses, sorry, and this is ribose now. So this is the code for ribose. Okay, let's see how we can write for ribose. I know I should have my aldehyde backbone already. Okay, whenever I see A, this is what I'm going to first write. Okay, then ribose to tell me that I'm dealing with ribose. 5 number of carbon is 5, so I have one already. 2, 3, 4, and the fifth one attached. Then the position, this is R, meaning right, and A is all. That means all the OH group are to the right, or the OH group are to the right, and I know automatically the other side is a hydrogen, and this is ribose. Okay, so next one is Arabinus, right? Arabinus is A also, meaning I'll have my aldehyde backbone already written. Okay, then R to tell me that I'm dealing with Arabinus. 5 carbon. Okay, I have one already. 2, 3, 4, and the fifth one attached here. Okay, then L2, meaning my position of difference is left in carbon number 2. Okay, then left carbon number 1, carbon number 2, I have to the left, and I know all the remaining carbons, my OH is to the right. And at the same time, I know the remaining position I filled with my hydrogen, and this is Arabinus. Okay, so next one in this category is Xylose, right? And I know when I see this my A, I know this is my aldehyde backbone to be first written. Xylose to tell me this is xylose. I'm dealing with 5, that is 5 carbon atom. So I have one already, 2, 3, 4, and the fifth one attached. Then my point of distinction, L3, that is left in carbon number 3. So I have 1, 2, 3 is left, and then I'll go back and fill all the remaining OH group must be to the right, and I know automatically hydrogen will fill the remaining. Wow, it's quite interesting. You see how the TNCP code is always helping me to have my sugars at ease. So next category are the hexoses, right? Those glucose, right? The key sugars that we always deal with. So the hexoses, glucose, right? And this is the code A-glu-6L3. We already created this, but let's do for it again. I know when I see A, my aldehyde functional group first. My aldehyde functional group first, my aldehyde sorry, I'm referring to my aldehyde backbone first. Glue to tell me that I'm writing for glucose. 6 carbon number 6, it has 6 carbon, that means I have 1 already, 2, 3, 4, 5, and the sixth one attached. Okay, so I know L3, that means my position of difference is left in carbon number 3. So I have 1, 2, 3. I have it to the left. Then all remaining, I know my OH is to the right, to the right, to the right, and automatically I know the remaining position is filled with hydrogen, and this is glucose. So next one is mannose. I have this code for mannose. So A first stand for the aldehyde backbone, the aldose backbone. Okay, then man to tell me I'm dealing with mannose. Then oh, I miss the number of carbon must be 6, so here is 6. Okay, so I have 6 here as the number of carbon, so I fill it to 6. Okay, 1, 2, 3, 4, 5, and the sixth one here. So then the point of difference, is L2, that is left in carbon number 2, and left in carbon number 3. So I have L2, L3, that is left in carbon number 2 and 3. Okay, 1, 2, I have left here, carbon number 3 left also. So under the remaining carbons, I will have my OH attached to the right, and I know automatically my hydrogen will fill the remaining space. So the revised form, the revised one will be A man 6 carbon L2 L3. Okay, yeah. So next one is the galactose, okay, and this is the code for galactose. Basically I miss the number of carbon, which is 6 here. We are going to have a revised one for it. So the revised one for galactose is a gal 6 carbon L3 L4. You can practice it as well. So let's write A. I'll have my aldehyde backbone already. First and last carbon are always the same. Then what? Galactose, to tell me I'm dealing with galactose. 6 carbon. It have 6 carbon. Okay. 2, 3, 4, 5. Next one attached. Then the position of difference is L3, L4, meaning left in carbon number 3 and left in carbon number 4. So I have 1, 2, 3, and it's to the left OH, carbon number 4 OH to the left, and then all the remaining are to the right. And I know automatically when I finish fixing my OH group, then automatically that position will be filled by the right. Okay, so this must be a mistake here, or this hydrogen. Okay, yeah, this hydrogen, not OH. The OH group cannot attach to the same sugar. So this is how I use the TNCP code to play around with all those monosaccharides, all those structures of sugars that you see me using. Okay, so now for ketosis. The configuration of ketosis, I use similar code, the TNCP code. Okay, technical problem. I use similar TNCP code to also write for ketosis, but there is a distinction. And of that distinction is that instead of this type for aldehyde, as I'll tell you, aldehyde, I use A, but for ketone, I use K. Okay, so whenever I'm writing for ketone, I know the first alphabet is K. So now let's look at this ketosis, ketose monosaccharide. The first carbon, look at this first carbon for this molecule, methyl hydroxyl group. Look at this first carbon, methyl hydroxyl group. Look at this first carbon, methyl hydroxyl group. Look at this second carbon, a carbonyl carbon, okay? And this is the ketone functional group, a carbonyl carbon, okay? A carbonyl carbon, right? So that means the first two carbon always for ketosis is CH2OH and a carbonyl carbon. Okay, so let's go to the last carbon. So the last carbon is always CH2OH, methyl hydroxyl group. So that means we already observed this in aldoses, so it's also the same for ketosis, right? So I know anytime that I am basically writing the structure of ketone, I know the first two carbons are something like this, and always the last carbon is something of this nature. So the only thing I want to know is where is the position of the hydroxyl groups that make that specific monosaccharide different. Okay, and we actually know how we can find that, because we assume that always they are to the right. Majority of them are to the right, and that means if we can know that distinction that is to the left, we can basically write the structure of the sugar. Okay, so but there is something in ketosis. For example, in this P, which we use to refer to code of difference, code for position, which I use to show the position of the hydroxyl group. So in some ketosis like dihydroxyacetone, there is no free hydroxyl group. There is no hydroxyl group for us to make that distinction. And if you remember from the TNCP code, if there is no hydroxyl group, what do I use? I use N to represent that code, and N is for known, right? So in ketosis, our TNCP code have the use of N, that is known. There is no hydroxyl group. Okay, so I don't have any confusion. So let's see how we can basically use this TNCP code to write. So the first one we are going to write is this offering here. So a technical problem, dihydroxyacetone, right? And this is the code that we created for it. Let's write for dihydroxyacetone. K, I know is for ketone backbone, right? So I have my ketone backbone already here. And another ketone backbone, the first carbon and the second carbon are something like this, and always the last carbon is something like this. So anytime I see K, this is the first thing that comes to my mind. Then DIH, which means dihydroxide. You know, in the previous code, I use parts the first three letters. Then 3, meaning it have how many carbon atom? 3 carbon atom. So I have 1 already, 2 already, and 3. I mean, I just need to join them. Then N means what? We know I use N when there is no hydroxyl, no free hydroxyl group. Okay, and that means this is enough as a structure of dihydroxy ester. So this is dihydroxy ester. Okay, so next one is xylose. Okay, this xylose, and this is a code for xylose. So right for it. The first thing is K, which I have to bring my ketose backbone, which is something like this. The first carbon and the second, and then the last carbon is its nature. Okay, this xyl to tell me that I am writing for xylose, sorry, and then 4, meaning it have 4 carbon. So I have 1, 2 already, then I need 3, and then join this. Then the position of difference, meaning L3, that means L left at carbon number 3. So in carbon number 3 I have, and I know automatically if there is any remaining OH, then it's to be right, and in this case there is no, so automatically this position will be filled by my hydrogen. So next one is ribulose. Okay, so this is ribulose, and this is the code for ribulose. So I have K here, then the first thing that comes to my mind is CH2OH bonded to this carbonyl carbon, and the last carbon is always something like this. Okay, then rib to show me that I'm writing for ribulose. It's almost similar with ribose. Okay, so basically when I have A rib, I know A ribose, K rib I know is ketose ribulose. So they are almost same compound. The only difference is that ribose is an aldose, it have an aldehyde functional group, and ribulose is a ketose, it have a ketone functional group. Then the number of carbon is 5. So I have 1, 2 already, 3, 4, and the fifth one attached here. Then R, that means my OH group are to the right, and all of them. So all those remaining carbon, I have my OH group attached there. And when I have those OH group attached there, then automatically I know the opposite side is my hydrogen. And this is ribulose. The next one is fructose. So how can we basically write for fructose? Let's say. Then K, I know I will have my ketose backbone, CH2OH, bonded to this carbonyl carbon, then the last carbon is always something like this. Okay, then fructose semi-ion, this code belongs to fructose 6, it has 6 carbon. So I have 1, 2, 3, 4, 5, 6 here attached, right? My point of distinction is L3, that means left in carbon number 3. So I have carbon number 1, carbon number 2, carbon number 3, OH to the left, and now all the remaining carbon will have OH to the right, and now automatically the other side is filled by hydrogen, and this is fructose. So see, this is almost similar with glucose. Yeah, it is the counterpart of glucose. So basically you see how this code is helping me to, and this is basically what I use during my undergraduate days. This is something I see in any textbook or any website or any journals, but I just try to be creative to bring something that will help me to master all those things that you say, which I'm sharing with you. So what you do now to master, to have perfection in this TNCP code, you have to try for as many sugars as possible, and I will assure you that you will become perfectly induced in writing the structure of monosaccharides using Fitcher projection. And automatically when you know writing Fitcher projection, then the Harworth projection will be quite very easy for you. So next part of this video, is Arabinus. Okay, so basically when we say Arabinus, we are referring to monosaccharides or sugars that differ in their configuration around a single specific carbon. A single specific carbon apart from anomeric carbon. So what does this anomeric carbon mean? We're going to see that one later in this video. So what does this explanation of Arabinus actually mean? When we say Arabinus, basically let's have these sugars. I have glucose here, I have mannose here, I have galactose. So what Arabinus is saying, when two sugars differ in their configuration in one carbon, and that carbon must not be anomeric. So what does this actually mean? So I have, for example, let's look at glucose. Glucose have, okay, let's look at glucose and mannose. The first carbon of glucose is this, similar with mannose. Okay, the second carbon is OH is to the left here. Okay, sorry, OH is to the right in glucose, but in mannose OH is to the left. So we have the first distinction, the first difference in this carbon. Okay, so let's see. In the third carbon, OH is to the left for glucose, OH is to the left for mannose. In the fourth carbon, OH is to the right in glucose, OH is to the right in mannose. Fifth carbon, OH is to the right, OH is to the right. Then the last carbon is always the same. So that means the only position that these two sugars differs in their configuration is in carbon number 2. That means glucose and mannose are epimers at carbon number 2. That is just what epimers are. Sugars that differ in configuration around a single specific carbon. So let's take another example between glucose and galactose. So let's have a look. Okay, let's delete this. Let's delete this so that we can have a clear view between glucose and galactose. So in the first carbon of glucose, sorry, I have this. Galactose, I have this. Second carbon, OH is to the right, OH is to the right. The same here. The third carbon, OH is to the left for glucose, and it is also to the left for galactose. In the fourth carbon, OH is to the right for glucose, but is to the left for galactose. So I have this difference now in carbon number 3, right? Then, okay, sorry, in carbon number 4. Then carbon number 5, OH is to the right in glucose, OH is to the right in galactose, and the last carbon is always the same. So the only point of distinction between glucose and galactose is in carbon number 4, meaning that glucose and galactose are epimers in carbon number 4. So this is basically what epimers are. So next part of this video we are going to see are called anomers. I will basically say anomers. Anomers are the alpha and beta form of sugar. Alpha and beta form of sugars. That's just what anomers do. And how can we know how is an anomer form? How can we have alpha and beta form? So what happens is that there is a kind of reaction between the OH group in the second to the last carbon, which I call the ultimate carbon. This is second to the last carbon, right? Which I call the penultimate carbon. The penultimate carbon. Okay, so this OH group in the second to last carbon, if you can see in all those sugars, it is to the right, and that is why we call all those sugars as D, right? It will react with the functional group of the sugar. So in this case, because we have two kind of functional group, for example, we can have either an aldehyde functional group or a ketone functional group. For example, either an aldehyde functional group or a ketone functional group. So in aldehyde functional group, there will be a reaction between the second to the last carbon and the first carbon with the aldehyde functional group. And if this happens, it will lead to the formation of something called hemiacetal. And when it is this second to the last carbon with the ketone group, it will be a reaction between the second to the last carbon and the second carbon of the sugar. And what will be formed is something called sorry. And what will be formed is something called a hemicara. So let's basically see what happens in case of glucose if this kind of reaction happens. So let me have a glucose backbone here, carbon 1, carbon 2, carbon 3, carbon 4, 5, and the last carbon. Okay? And what this is the kind of reaction that is going to happen. I have an oxygen bridge here, and then I will have this bond attached. Okay, so this carbon and this carbon, right? So I have this second carbon, it will be arranged as the same as it is. The third carbon will be arranged as the same as it is. The fourth carbon will be this way, and then the last carbon is always untouched. So if the OH group is attached to this right side, that means automatically the hydrogen will be here, and this is called alpha D glucose. So when the OH group in this carbon, and this carbon is called what? This carbon is called the anomeric carbon, and this is the anomeric carbon we are talking about. Anomeric carbon. So when this OH group is attached to the right, like in this case, it is called alpha D glucose, alpha sugar, alpha galactose, any kind of sugar. But when this OH group now is attached to the left, as in this case, this OH group is attached to the left and automatically hydrogen is to the right, then it is called beta D glucose, right? So you see, it's the same glucose, but the only difference is the position of the OH group in this anomeric carbon. But in this regard, they are not called epimers, but rather they are called anomers. Okay, so this is basically what anomers are. Anomers are the alpha and beta form of a monosaccharide. So they are the same compound, but the alpha will have different rotation of the plane polarized light, and the beta will have a different kind of rotation of the plane polarized light. So this is alpha D glucose, and this is beta D glucose, because OH is to the left and that's why it is beta, OH is to the right and that is why it is alpha. And both these two monosaccharides have different optical activity, and this is what we are going to use in writing the Harworth projection of monosaccharide. So in the next video, I'm going to show you how you can basically write these structures into the 3D Harworth projection. Okay. Alright guys, that's it, and that's what we have for you. Please stay tuned to our channel, like, share and subscribe. We are going to make biochemistry and other related life science courses very easy for you. Stay tuned to this channel. See you next time.